Who was here in September of 15 to hear me talk about the New Horizons instrument? So, okay, we got a few. And how about January of 17 when I talked about occultations? Yep. Okay, so the cool thing about this talk is if you've seen either one of those, you're going to be bored out of your mind because this is a combination of the two, sort of. So the quick story, backstory, is as a hobby, I time occultations to measure the size of asteroids, and sometimes we get really lucky trans-Neptunian objects, TNOs, the ones way out in the outer reaches of the solar system. And that's been my hobby for 10 or 15 years in astronomy. Regular astronomy before that, before I got really specialized. And in the meantime, of course, I build instruments that go on spacecraft. Well, back January of 17, in fact, about the same time as I talked to you guys last, there was a New Horizons science team meeting at Johns Hopkins. And as an engineer, I tend not to go to the science team meetings, but a couple of the scientists from our principal investigator institution at Southwest Research out in Boulder, Colorado were there, and they called me over to have lunch with them. And it's like, okay, what do these people want to have lunch with me for? You know, I'm just a peon engineer, and these are famous scientists. So anyway, they sit me down for lunch and they say, okay, so New Horizons is going to a Kuiper belt object that we're going to get to next year. We'll talk about that a little bit later. And we want to measure the size and shape of this object before we get there. And the reason they came to me is they knew I did this as a hobby. And they were asking me to recruit a bunch of my fellow amateurs who do this to get everybody to go down to Argentina a couple of times and try to do this on this target we're going to look at. That's what I'm going to talk about tonight. So it was really another interesting coming together of my hobby and my work life. And if you may have remembered from before, how I got into this job was I was rubbing glass. I was grinding mirrors starting when I was 13 years old in my basement. And that developed my love of optics and how I got into this job. So that's how I got into the job, and now my hobby and work life come together again. So New Horizons spacecraft, you guys are aware of that. We went by Pluto July of 15. It seems like a long time ago now. It has been. After we went by, well, actually before we went by, we'd always sold this mission as we wanted to go by and look at some Kuiper belt objects. After we went by Pluto, we had the thought of maybe we could even go to 2 if we got really lucky and they were aligned. And we thought, well, there's going to be a whole bunch for us to choose from. When we launched in 06, we thought we'd find them before 15, right after we went by Pluto, and we'd have our choice of where to go. You know, we'd use some of our fuel to deke off one way or another and go by another one of these objects. Turned out these things were a lot harder to find than we thought they were. So they used, you know, all the big telescopes on Earth, a lot of observing time, looking at that little patch of sky that we could get to with the amount of fuel we had, and found nothing. So in 2014, they went to Hubble and they said, please, please, please give us a whole bunch of orbits to look for one of these guys. And that's what we did. And they looked really hard. They used a lot of orbits of Hubble time, looking as deep as they could possibly go, and they found 3 candidates. One of which they decided was a little bit too far out of the cone we wanted to use, how much fuel we wanted to use. Another one was towards the edge, but doable, and then there was one near the center where you didn't need to use much fuel. That was a little bit fainter than the other one, and it was decided to go to that one. So we would use the least fuel, with the thought also being that, you know, we went to one of the biggest Kuiper belt objects, Pluto and Charon and all. Let's go to one of the small ones and see what the small ones look like. So the right picture there is the discovery photos of MU69, now referred to as Ultimate Thule. We had a contest involving naming, or ceremonial naming, not IAU official naming of what this target is. But you can see, you know, the 5 images going across here of the 5 different Hubble exposures when we found this. So let's talk about MU69. So it's a small Kuiper belt object. As I said, it was discovered in 2014. Magnitude's 27. Never been seen from the ground. Keck, all those other telescopes, never seen it. We're going to fly by January 1st of next year. Closest approach will be about 1/3 the distance as we went from Pluto, so it's going to be a lot closer. We're going to get 3 times the resolution, roughly. By the way, don't invite me to any New Year's parties for next year because I'm busy. In fact, I'm busy Christmas too. Our encounter period starts on Christmas Day. So this is going to be the first time in my life I've missed Christmas with the family, but that's the way it's going to be. So Kuiper belt objects can be very bright or very dim, albedo, how white or dark they are. They can be almost as dark as charcoal. They can be almost as bright as snow, sort of like the contrast we saw on Pluto. So when Hubble was looking at it, Hubble can say, we know how far away it is, and we know how bright it is, but that doesn't really tell you a lot about how big it is, right? If it's a really white object, a snow-like object, it would be really small. And if it's a charcoal-like object, it would have to be really big to reflect that much light back to Earth. So we didn't know anything at all about the size of this object other than saying it's somewhere between 10 kilometers and 40 kilometers. So it's a factor of 4. It's a big difference. So viewed from Earth, that's 1,000th of an arc second. There's no way Hubble can resolve it or any of the ground-based telescopes. It's like looking at an orange from 13,000 miles away. That's what we're trying to image. And here's why it matters. So my New Horizons instrument has a field of view of about 1/3 of a degree square. So that's what the squares, the red squares are. If MU69 was only 10 kilometers across, well, we go by it at 3,000 kilometers away. If it's the bright target and small, I could take one image of it and get everything in there. If, on the other hand, it's 40 kilometers across, we'd have to do a mosaic to get all the surface of it when we're as close as we can. So you can see that it's important for us if we can know in advance how big this target was. So we were motivated to know more about it. Other potential issues is it could have an unusual shape. So we went to Eros, the asteroid, and that was shaped like a big, almost like a big boomerang shape. And we could also have debris fields, like we were worried about at Pluto. Could it have a ring? There's several objects out there already, like the Senator Charlico, or however you pronounce that have been found to have rings. So you could imagine New Horizons coming through there. We're trying to fly close, and if we're trying to fly close and we go through a ring, that would be really bad for your spacecraft, right? So the problem is it would be really beneficial for the New Horizons encounter next year to know in advance the size and shape and or if there was any debris issues at this little Kuiper belt object. But the ground-based telescopes can't even see it, and Hubble only sees it as a dot. So Hubble can't help us, ground-based telescopes can't help us. So what other properties could we take advantage of to find something more about MU69? And the answer is occultations. So even if the Kuiper belt object is too small to directly image, it still casts a shadow on Earth. I should put shadows in quotes there. So if it's backlit, if there's a bright object behind it, far enough behind it, and just imagine there's a world's biggest spotlight behind this thing lighting it up, you can imagine it projecting let's say it's a 10-kilometer object, a 10-kilometer spot on the Earth. Well, we have objects like that. They're called stars. So when the Kuiper belt object would go in front of a star, it'll blink that star out for a short time. And if you can measure the blink with a number of different lines, you can measure the size of the object. So here's how it works, and this is a chart I did show last January, because I show it every time I talk about occultations. So imagine that you have an asteroid that's casting a shadow on Earth. There's the shadow path, we're going to make pretend. And it goes across the US and Canada. So we have observer A, who's in Edmonton, Canada. We have B in New York, C down here in Kingsport, D in Atlanta, and E in New Orleans, or something like that. So what would each of the observers see? So the guy up in Canada, if he's looking at that star, he would just see the star the whole time. It would never blink out. It would never get blocked by the asteroid or the Kuiper belt object. Where the person in New York would see a short blink, right? When the asteroid went in front of the star. The person down here in Kingsport would see a longer blink. Atlanta would see about the same as here, and the person down in New Orleans would not see any. So with that information, you can say, well, I know the asteroid or Kuiper belt object shorter than from here to here, and I know how wide it is here, here, and here. So you can sort of make a line drawing of that, right? And measure the size and the basic shape doing that. And by the way, please interrupt with questions at any time.
Well, I've already got questions.
You want to interrupt now or later?
Now, because I'll probably forget it later.
Go ahead.
Okay, so what you're saying is you're taking the distance between A and E, and then you're using that distance and start going backwards with the distance between A and B, B and C, and C
Well,
and D.
let's think about what we have here. So let's ignore A and E for the moment,
Okay.
and let's just worry about B, C, and D. So we know that you have a dot here and a dot here, right? That you know that there's an asteroid in between. You have a dot there and there, and a dot there and there. So I can do this and say I know how wide it is here, and it's at least this long. And then I can say A and E, I know it didn't go, so it's shorter than that. So they constrain it. They don't tell you exactly, A and E don't tell you exactly how long it is, but they constrain it, and you can say it's no longer than, I don't know what that would be on Earth, thousands of miles. That's a crazy big asteroid, but that answer it?
Yep.
Okay.
And so you have to know the distance to the object, though, to really help
Yeah,
constrain the
and
size.
that is easy stuff. That you get from orbital. So, you know, it's funny because for something like this, we know the distance very well, you know, down to thousandths of a percent or something like that. But interestingly, for the flyby, so when we're going by this object next January, our biggest unknown that we worry about is how far it is from the sun, when we're going to go by it. So, you know, think about it this way: is if you're measuring just a tiny little bit of its orbit. We found it in 2014. It has a 300 and some year orbit. We've just took more Hubble data this past week. So what do we have? We have 4 years maybe of observations of 300 all the way around. So we don't have a really good distance.
That's certainly enough to give you an orbital path to predict what stars it'll include.
Oh yeah, yep, yeah. That's you get 2 dimensions very well, right? So you're looking at something. I know which direction it is in this plane and which direction it is in that one. It's in and out that I don't have good information on. But like I said, for this, it's good enough. When we fly by, that means you have a time error. So when are we really going to fly by? When we're coming right at it, it doesn't matter. But let's say you're the object, okay? You mind? Now, here I am on my spacecraft. I'm going by, and I want to take really close pictures when I go by. Well, I don't know if he's here or there. So when do I take my pictures? So what do is you say, the furthest he could be is here. The furthest he could be that way is there. So as we go by, we're going bing, 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 all the way down like that. So we're going to take thousands of pictures. And a lot of them are going to be blank sky or just stars. But You know, you want to get the best resolution, that's all you can do. Okay, can I go on? Anything else? It's easy to get me off on tangents, by the way. Go ahead and try. All right, so in order to get the data we need from this occultation to measure the size of this Kuiper belt object, what do we need? We need to have enough stations across its path. You know, if we only have one station across it, one blink out, all we know is one chord, one width of it. We don't know anything about the other dimension. We don't know if we're on the tippy little bit of the bottom and it's a huge thing, or we're right through the middle and it's a smaller thing. So you want to get at least 2 stations, and usually more like 3 or 4, to get a good idea of size and a little bit of information on shape. You need to collect data. You need to take pictures quick enough you can see it blink out and be blinked out a few times, because each one of those blinks gives you resolution along it. So if you only had one image that didn't have the star, you don't know very much about how that width is. If you have 30 images, you know, it could be plus or minus 1, and that really constrains the width in that one chord very well. So you need to have a number of stations across, and you have to take images fast enough to have resolution that way. You need to have enough signal so you're sure if the star is there or not, signal to noise ratio. So you need to count enough photons that you know the star's really there or not there. And you have to get your time very well. You have to know your camera's time, when it started taking the picture and when it stopped taking the picture very well. We use GPS for that. And of course, you need to know where you were on Earth. Well, again, GPS makes that really easy, or just even picking your spot off a map is fine for that one. Okay, occultations of Kuiper belt objects. We knew that at the most, if the object was 40 kilometers across, it would blink out a star just for a couple of seconds. If it was smaller, it would be shorter. We need to take, like I said before, take enough pictures over that time to get some resolution of the size. So you want to get several images of it being occulted. So you need to take rate pretty quick, give us a rough measure of the size. And the potential paths of these objects can occur anywhere on Earth at any time. So they can happen in daytime, and you can't take data in daytime, obviously, of a faint star. They generally go over the most land area where they are in declination. Okay, everybody knows what declination is in the sky, right? Sort of like the equivalent of latitude, right? Latitude, yeah. So north and south. This Kuiper belt object is like at minus 25. So most of the occultations for it would be occurring in the southern hemisphere. And sure enough, that's where they happened. So they don't happen necessarily over observatories. So you're lucky when they happen over observatories. It doesn't happen most of the time. And we need a tight spacing. We need kilometers apart, a few kilometers apart, 5 kilometers apart, something like that, 3 miles. So you need to have enough stations to cover that. Oh, and we don't know where things are very well. We don't know where this object is, and we don't know where the stars are, surprisingly, very well. So that puts a huge error on that path. Remember the path I showed you? Imagine that path is 3 or 4 times the width of the object. So now you have to cover, say, 100 kilometers with a spacing of a few kilometers, maybe 5 kilometers. You're not talking you need 20 observers across the path. And you have to have good weather. So all that together effectively makes you use portable equipment. And you need to be able to set it up, you know, somewhere along that path so you have the whole thing covered. Oh, I'm already getting ahead of myself. Okay. So New Horizons team and some other groups around the world that specialize in these things were trying to find occultations for MU-69 for years, well, for 3 years. And in summer of 17, they found there were going to be 3. All 3 crossed South America. One also crossed the southern part of Africa. The second event only had a little bit over land in the northern part of South America in an area where it's always rainy that time of year. Thinking Colombia or something of that sort. So that one they decided that they wouldn't pursue with a ground-based campaign. The stars for these events were anywhere between 12.5 and 15.5. And for occultations, 12.5 is a faint one for those of us who do this as amateurs. 15.5 is crazy faint. It's really hard to do. Yeah, and there was relatively large error bars, like I said before, because we didn't have a lot of data, and we don't even know very well where the stars are. So here's the 2 events we decided to pursue, event 1 and 3. And you can see the first one crossed the tip of southern Africa, and then middle part of Argentina, and then Chile as well. And then the second event in July just went over the very southern part of Argentina. So to cover the whole potential path, we wanted 99% confidence that we get a positive measurement. We need to cover about 100 kilometers, we thought. And again, 5-kilometer spacing, that's how you come up with 20 people, 20 stations. And these stations, by the way, I'll show you in a minute, were 16-inch telescopes with a lot of equipment, and there were a lot of old guys like me, so we had to have some young people with us. So we ended up saying that we needed 2 people per station. So now we're up to 40 people. And then there's all the logistics people, so you really end up with 50, by the way. So occultations with portable equipment. Well, us amateur astronomers are used to traveling to dark sky sites. I'm sure a lot of you guys go to, where's your local dark sky star party down here? You guys go to Green Bank, Virginia, West Virginia, or something like that, or no?
What's that Southern Appalachian? Anyway.
Okay, but a lot of people are used to throwing their equipment in the car and driving off to some state park or whatever and observing there. So us amateurs, and here I'll consider myself to be an amateur rather than an engineer, are used to doing that. I do that myself. We typically, at least when I go, I'll bring my 9.5-inch telescope. But typically go to Star Party. Most people have 8 to 12-inch telescopes. Maybe once in a while you see somebody with a 24, or I've seen a 30 or 2 in my lifetime at Star Parties as well. But those big telescopes are really hard to ship. Even my 9 or 10-inch telescope's a pain in the neck to ship. So we thought the largest sort of shippable telescope we could come up with was a 16-inch Dobsonian. That aperture combined with a low-noise CMOS camera would enable us to see the fainter occultation with a 2 hertz frame rate. That means 2 pictures per second. So we don't get really good resolution across it when we're doing at that rate, but that's what we needed to do. Here's the equipment. So it was just a regular Skywatcher Dobsonian telescope. These are go-tos. The Skywatcher people were pretty freaked out when we told them we wanted 22 of these. They normally, I think they said they sold about a dozen a year. So we had one order of 22 from them. And then the QHY camera, which I have one here. In fact, this is a spare. This is my personal camera that I sent down to South America as a spare. Didn't get used, but it made the round trip. In fact, for those of you who know what NEAF is, in a couple of weeks, the Northeast Astronomical Forum, big vendor show of telescopes up in just north of New York City. One of my friends was up at that show, and she knew we were going to be using that telescope for our occultation campaign. So she brought the floor model so we'd have one so we could practice with in the Northeast, since all the other folks were out in the Denver area. So the equipment we had Again, 22 Skywatcher Dobsonians. We also sent down several telescopes that were actually from the University of Virginia. They sent a couple of their C14s down, and they also have a portable 24-inch that they sent down. The Skywatchers, like I said, are 16-inch f4s for those who care, and they're go-tos. So you've aligned to 2 stars, and then you can find an object just by going to ARIA and DEC. The QHY Camera is a CMOS device about the size of a postage stamp imager, if you care. A little over 2 megapixels, and you can get more than 10 frames out per second. Of course, this time we're not going anywhere near that. The big thing is it's got a GPS built into it, so it gets time from the GPS satellites, and each picture it stamps with the time to a millisecond. And then the other thing we needed was laptop computers. So every team also had a laptop like this. The team was a really interesting part to me. So Southwest Research Institute, the PI, Principal Investigator Organization for New Horizons, led the campaign. We needed about 50 people. There are professional astronomers who do occultations, but there's probably about a dozen in the world. It's not a big thing for typical scientists to do. They also pulled in other scientists who didn't have occultation experience. They pulled in other team members from New Horizons, professional astronomers and engineers with no experience in this, but they still needed more experienced people. So they came to me, like I said at that lunch meeting I started on this with, and asked me to recruit about 12 people. So we sent about 12 IOTA folks down there. Actually, on the first trip, half of them went to South Africa and half of them went to Argentina. I went to Argentina. And since half the team, 2/3 of the team, had no experience, we had these boot camps. So there was a boot camp out in Arizona, a boot camp in Colorado, and a boot camp in my backyard. And I had people drive to my house from as far away as Atlanta, Cleveland, and Boston. I live in Maryland. To come for one night to learn how to use these telescopes. So when we got to Argentina and we only had 3 nights to practice, they would have a leg up. Pretty dedicated team. And like I said, it was really interesting when the scientists some of the scientists didn't realize our experience level, and when they saw what we could do compared to what the inexperienced scientists could do, they really learned to team up with us in a hurry. Again, the 3 campaigns. Campaign 1, we sent 11 stations to South Africa and 11 stations to Argentina with about, 12 in each place. Event 2, we used the Sophia airplane, the airplane with the big telescope on it, out over the Pacific Ocean and a few fixed observatories. And then event 3, where it only crossed the very southern tip of South America, we sent everybody to southern Argentina, all 24 teams. So here's just a few photos from the first campaign. We're headquartered, the Argentina team here in Mendoza. If you know Argentina, that's like the wine growing area of Argentina. Mendoza is a tourist town. They're the Andes to the west. That's what downtown looks like. Fairly modern city, a lot of parks, really nice. But as soon as you get out of the city, you run into areas like that. There's unpaved roads, rutted roads, nobody, not anything. Other than bugs, you don't really see much living thing at all. And then I have my picture of my pickup truck that we rented. And one of the big challenges was renting enough pickup trucks in Argentina, in these little cities. They had to bring them in from like Buenos Aires and all to have enough. But the pickup truck we had was like the equivalent of a Toyota Tacoma with the long cab. So it had the short bed, and every inch of that bed was filled up with telescope mount, and other equipment. That vehicle was just completely filled. And the interesting thing is down there, Toyota Tacoma is a big vehicle. So like this is parked in the hotel, the garage under the hotel, and there's just barely enough room around the concrete columns to park a pickup truck. And that's, Tacomas are what, mid-sized pickup trucks or smaller ones. So it was a trick just getting around the city. And then campaign 3, we went back down a month and a half later. We went down to, I'm going to butcher the pronunciation, I think it's Rivadavia, Comodoro, which is an oil drilling city on the coast, way down. Now, this is July, middle of winter down there. This is at minus 46 degrees latitude, which is further north than Montreal in the north. We were right on the ocean. Rivadavia its nickname is Queen of the Winds because it's always a 25-mile-an-hour wind down there, always. So here I took a picture from a bluff looking south. The rich enclave is here in Argentina, and then once you get past that, there's just nothing for hundreds of miles. Because of the wind, we had to improvise tarpaulins to try to keep the telescopes from blowing around. Telescopes act like a big sail. And we were really lucky. The assigned location we had, when we went down to the beach, we found a old industrial crane. Apparently there was a port there during like World War II or something. And this crane framework had fallen off the concrete pier. So this metal frame box was just laying on the beach like this. So we tied all our tarpaulins around that and made a box to protect our telescope from the wind. Here's the team. I'm on the left there, my teammate here, and then we had students from Argentina helping us, tactus translators and things like that. And the student took this picture of the Milky Way. The heart of the Milky Way was right overhead. He took that handheld. It was just, the Milky Way was so bright and stunning, like I just wanted to do, Steve, you need to get to work. And I'd be just looking at it. So it was miserable because it was cold all the time, but the skies were beautiful. The Argentinian people and the Argentinian government were just so incredible as helping us, and especially the second city, the oil drilling city. We were treated like heroes in that town. One of the scientists and I went to lunch at an Irish restaurant, the only Irish thing on the menu for those who may know Guinness, what Guinness beer is. That's the only Irish thing they had on the menu. But it took us 3 hours to get out of there because people kept sitting down and saying, Americans, NASA? And they'd all want to talk to us. And we just couldn't get out of there. And we were in the paper every day. We ran into things like each state in Argentina, they have border checkpoints between the states. Imagine if the US was like this. When I drove down today from Maryland, when I crossed from Maryland to Virginia to West Virginia, back to Virginia in 4 miles or whatever it is up in Harper's Ferry, I would have had to stop at this checkpoints each time. But we went to checkpoint coming back, or going down the first time, crossing state lines, and the big thing they were worried about was, were we carrying any fruit with us? When we went back, the big thing they were worried about was the other state we were going into required your headlights to be on during the daytime. And we didn't have our headlights on. So the border guys were like, another ticket we're going to issue here. And we pull up, and they're talking to us in Spanish, and neither of us talk Spanish. And after a minute, they go, Americans, NASA? They start laughing and go, go. So we got out of jail a couple of times, and we did have other things that happened that weren't so good. It was good we had Argentinians with us to translate and explain to people who didn't know who we were why we were there. So here is the path of the second event. Again, going over the very southern part of Argentina. Here's zoomed in. This is to show you what our stations look like and how we set people up. So the path went right over the city. So we were lucky about that because there really aren't any cities north or south for hundreds of miles. And you can see our spacing. So each one of these yellow pins is one of our stations. And the path is mainly left to right or right to left. So, rather than putting people in the center of the city, other than one station, we put them out in the suburbs here, and then going way up. And for the second event, I was all the way down south. So I was the southernmost person here. And like I said, the spacing's like 5 kilometers, but I had an hour and a half drive or something from the hotel. So the results. So despite thinking we had a really good shot on event 1, we did not get any positive from event 1. And after they took additional Hubble photos of where it was after the fact, they adjusted the orbit and they found we were all too far north. So the path went south of us by, I forget how many kilometers, 20, 30, 40. Event 2 with Sophia out over the ocean also initially did not show anything we believed was a positive. But it did show, we were confident enough in that data that we knew it didn't have a strong ring system, a debris field we had to worry about. So there was a positive from that observation in that we got that information. But event 3, we had a success. So we had 5 chords across the object. We have a really good understanding of the Kuiper belt object shape and size. It's about 30 kilometers long, assuming it's a single object, we'll get to that, by 15 kilometers wide. We know what the basic shape is, and again, we've ruled out a strong ring field, debris field. So here's one of the positives. There's our star, watch it. It just continuously loops. So that's basically real-time observation. And the motion is all the residual wind they had. This wasn't my station, this was one of the stations that had a positive. Here's what the data looks like. So this is how much light we're seeing from the star, the signal level. This is time in seconds across here. So you can see it bouncing up and down with the noise of the measurement. And then they get here and it drops down to almost nothing. And then there's one intermediate point where it's partially in the frame. And it goes back to normal. So a very good data set. And then you can infer, let's go to the other one. I like the other one better. Here we go. From the 5 chords we have, we know it's this wide here. We know it's that wide there, that wide, this wide, and that wide. And we know it wasn't there or there. So with those 5 lines, you can draw anything you want that's reasonable between those points. Question is it one big weird shaped object like Eros asteroid I showed you earlier? Is it too close? Is it contact binaries? Are there 2 objects that are stuck together and rotating around like that? Is it 2 objects that are in orbit around each other and they just happen to be lined up like that when we saw it? Left a lot of questions, but I can tell you it's going to be really cool when we get there in January. It's not going to be just a perfectly gray little ball. It's going to have some shape to it. So get the artists involved, and what do they come up with? Here's your 2 objects in contact. Could be something like that. Or is it just a long, oblong thing? Now you might have seen this in Sky and Telescope a month or a couple months ago. They went back and reanalyzed the data after they did their analysis. And they put all the chords from all the events on there. So here we are up here, the first event where we missed. You can see it was way south of us. Here is the third event where we had the positive. You can see the outline there. When they went back and looked at the Sophia data, they found there was 1 frame where the star wasn't there. 1 frame usually you don't base stuff on. But when they looked at it in this way, it lined up with where they thought MU69 should have been. It should have been here, they thought, and ended up there. If that was a real moonlet, it really was a positive, but not the main body, it all lines up perfectly. So Is it a dumbbell shaped or a contact binary or two closely rotating ones with a little one rotating outside? We're going to find out in January. But it's just amazing the way that lined up perfectly like that.
Do you know what the distance is between the possible moonlet and the main object or objects?
Yeah, well, from this one, you can say that, this is 30 kilometers, so, it's 150 kilometers or something like that.
Can you tell anything about the rotation?
No. No, because you don't know what the planes are. And then if you've been following Sky and Telescope, in fact, there's the...
Orbit of its possible moon.
So here's the article about that from Sky and Telescope. And the vendors who supplied both the telescopes to us and the cameras had been advertising that they were part of this. So there's a Sky and Telescope ad. The Skywatcher people, I think, mentioned it in an ad, and also the people who made the 24-inch the University of Virginia brought, they mentioned that in one of their ads. So we're famous. Okay, closing comments. So through a lot of people coming together of all different flavors, scientists who do occultations for a living, other astronomers, other professionals on New Horizons that are willing to be trained, and a bunch of us amateurs, that team, that diverse team, we just did amazing things. Everybody was chipping in. I mean, we were working every night, and during the daytime, we were doing things like, oh, the scientists don't know how to collimate their telescopes? Let's go, IOTA guys, we're going to go collimate 22 telescopes, and that's what we did. We just had an assembly line, one mount, and we'd pick up the telescope body, put it in, collimate it in the parking garage of the hotel, put it back in the case, and get the next one. And we did that 22 times. The equipment we used was relatively inexpensive, off-the-shelf hardware that we were able to make this measurement that Hubble couldn't do, Keck couldn't do, but we could do it. And this data is really important to our planning for how we're going to image this when we go by it next January. And that's all stuff we're doing now. We can't make the change at the last second when we're getting up there. This all has to be pre-programmed. So we're testing right now what we're going to run on January 1st. Questions?
How far beyond the orbit of Pluto is this object?
This is at, I think, 42 AU-ish, something like that. So another 10 AU.
Beyond the Pluto's orbit?
Sorry?
42 AU beyond?
No, 42 from the sun.
42 AU.
It's 10-ish or so beyond Pluto.
Yeah, New Horizons is
No, we're fast. We're not that fast, yeah. Anybody else? Yeah.
That's coming in quick.
So, give a rough estimate. What would you say? So it's relatively inexpensive equipment. We're talking we're in about the.
When you buy telescopes in quantity, their price goes down quite a bit. And I think they were of order 2,000 or something like that each. These cameras, when I buy them, I don't know how much they paid for them, but I bought mine for 1,200-ish. Laptop computers are a couple hundred. And making shipping containers to get these all to South America. Making 22 custom shipping containers is not cheap either.
The vendors of the equipment didn't provide proper shipping containers.
They just sent them in their normal cardboard boxes. And you don't want to send stuff to South America in cardboard boxes.
So the equipment was paid for by NASA.
Mhm.
And so where is it now, and what's it going to be used for?
It is now in Boulder. I thought they may have sent a couple of them to the Triton occultation. You get folks aware of the Triton occultation that happened in October? So Neptune's moon Triton, the big moon, got occulted by a star. We know the size of Triton, so we're not really worried about the size or shape. It's circular, it's spherical, and we know the size, but it has an atmosphere. So the reason they really wanted to see that is they hadn't observed Triton in, I'm just going to pull a number out of there, something like 20 years. And when you have, is there chalk there by chance?
No, unfortunately.
Okay, so I'm just going to have to wing it. If a normal occultation of an object without an atmosphere is an on-off switch, more or less. There's diffraction and things like that, but don't worry about that. So you see the star, and it goes away, and then it comes back. If there's an atmosphere like Pluto or Triton, what you'll see is the star fades out, and then goes away, and then comes back in. And you get a slope, and if you measure it in different colors, the slope will be in different colors depending on what's in the atmosphere. But the really cool thing is if you're on center, and you go, this is Triton, and you go right through the center, when you're on center, that atmosphere acts like a lens. And suddenly the star gets really bright where it shouldn't be and goes away. And the scientists are able to do a lot of neat stuff with the data when they get the central flash. And they got a whole bunch of central flash data on Triton. Not these telescopes, because most of the US efforts got clouded out. The Europeans, on the other hand, apparently it was just perfectly clear over there, and there's data, there's like 200 stations of data from Europe. Wow, off on another tangent there for a second. Anything else? Yeah.
So you got a lot of inexperienced people doing this. Do you think you got some of your recruits? new amateur astronomers? Or?
We had, when we were really beating the bushes, we had a couple of amateurs who really had never done occultations before come on board, and we needed them. We needed the bodies, and we figured we could train them. One of them has become one of our big people now in just less than a year. One of the other guys, I haven't seen or heard from him since. But he was still incredibly useful during there because he knew telescopes. He knew amateur telescopes. He didn't do occultations, but he did have experience that was good to bring to the table. He was also an international traveler, and the rest of us weren't, so that helped too. Anybody else?
How's the spacecraft and all the instrumentation
Perfect.
and everything?
Absolutely perfect.
Yeah?
Uh-huh.
Wow.
Yeah, we're, like for example, my instrument has been now up there since 06, so 12 years, and it performs exactly the same now as it did when we launched it. We cannot tell anything different.
Is the door open, or do you open and close it? Or is it
Our doors are all one-shot. Well, I shouldn't say that. The door on my instrument is a one-shot door. So you pop it and you can't close it again.
I was just wondering, once you make it through the Kuiper belt, then maybe you'll come into the Oort cloud in the future?
Yeah, we'll run out of power long before that.
And what's the life expectancy of the unit?
Into the late 2020s, and then we'll probably run out of power. We only have one power generator where, Cassini, for example, had 3 of the ones. We have 1. You know, we have 200 watts. So our whole spacecraft's 200 watts.
So it won't be operational, okay.
No, but I will throw out that there's other science we're going to do with my instrument. We have been observing distant Kuiper belt objects. We've been doing a lot of them. So one big advantage New Horizons has right now is that we're at 40-some AU. Kuiper belt, sort of the heart of the Kuiper belt. You can look sideways and get a different angle of light coming off. Where if we're observing a Kuiper belt object from Earth, we're basically always looking in the direction the sun hits it and comes right back, right? We're only, I'd have to do the math, a couple of degrees or something like that of angle variation. We can look at them from 90 degrees. And if you look at the ratio of the intensity you get from that direction versus this direction, you can tell a lot about the surface properties. So we've been observing, I think we probably observed at least a dozen by now, distant Kuiper belt objects to measure that ratio using ground-based and using LORRI on New Horizons. The other really cool thing that one of the other scientists, I think a scientist not involved with New Horizons, thought of is, you know, cosmic background radiation, you know, that the 3K. Well, there's also visible cosmic background. And you can't measure that when you're inside the solar system because you have all the zodiacal light and all the scattered dust in the solar system. We're getting beyond that. So they've started to use our images of background star fields to see how dark the background is in the visible. So we're doing an astrophysics experiment now. You know, there's also things I want to do is I want to take a picture of a close star to Earth and then have amateurs on Earth take pictures of the same star and show the three-dimensional look to it. So that might come up if we can get that approved. Anybody else?
You said you can look at 90 degrees to the angle that we can see from Earth. Are you thinking about like looking at atmospheric effects?
No, surface properties.
Okay. I wanted to eliminate
This, how the scattering from the surface looks like, how rough the surface is.
Okay, so you're not interested in particle size in the atmosphere or anything?
We don't think, well, you shouldn't say this because we've been wrong every time, right? is little objects like that shouldn't have atmospheres, okay? But, you know, until a few years ago, they thought little objects could not possibly have rings, right? And now we've seen 2 or 3 of them that have rings. And 20 years before that, it was asteroids and Kuiper belt objects can't possibly have satellites, and now they're common. But I'm not a physicist, so I don't take credit for being wrong. Anybody else? Well, I enjoyed speaking with you all, and hopefully one of these days I'll get a chance to come back. I still have one more talk in the can you guys haven't heard, and that's about spectroscopy.
And of course, you'll come back and tell us about these results.
Oh yeah, that's true. So after next January, I'll be able to come and have just a zillion pictures of the same funny shaped thing in different aspects as it rotates around. And I am also now working on the Lucy mission. Anybody hear of the Lucy mission? So we're building another LORRI to go to the Jupiter Trojans, to do a survey of the Jupiter Trojans, which are asteroids that lead Jupiter in a Jupiter orbit by 60 degrees and trail it by 60 degrees. So we're going to do a sweep through the leading ones and look at a whole bunch of them, come back to Earth, and then go back out and see the trailing ones and take a whole bunch of images of those. And that gets launched in about 3 or 4 years. And I'll be long retired by the time it gets to the targets. So I won't be speaking about those. Thank you.
Steve, thanks for coming.